calculations on here.
So it means that they fall within what you would expect?
Yeah. We would say the distributions are normal based on the z-scores we would calculate.
Okay. So we're doing training group right here, so that would mean that neither of the training groups had a significant effect on learning or something like that?
This is just a test of normality. So both training groups have distributions that have a normal shape.
Or that are about normal.
Yeah.
Plus or minus, or less than 1 z-score away from normal.
But what does that mean?
It just means if we're analyzing these in a test that requires normality, we've passed that test. So
basically, results are what we expect.
No, basically the results are along a normal plot close enough that the standard analysis tool will work.
yeah.
So all we're doing is testing the data to see if it's looks reasonable enough to use a standardized test.
And a standardized test would be?
Well, it could be an ANOVA, it could be a regression.
All the ones would be.
Yeah.
Okay.
Anyone that calls
So
for
if it
normality.
wasn't, if it was significant, we couldn't use those tests, is that?
Well, we may be able to, but we would first have to transform the data. For example, we might have to compute logs on, say, the dependent variable.
I don't want to do logs.
Yeah. Well, fortunately, SPS will do that for you.
Yeah, that'll work then.
But we might have to do transformations depending on how large the deviation is from normality and how rigid that test is on the normality assumption.
So we talked about fit yesterday. Would you do this before you started crunching your data?
The proper way to do it.
Am I skipping ahead?
No.
Okay.
You're asking the right question, and I've done this part totally backwards from the way you're supposed to do it. And part of it is you can't really talk about assumptions very well unless you know a little bit about statistical tests. But in your study, you would test the assumptions before you start the analysis.
Before you do the stats.
Yeah.
Okay, that makes sense.
And if you don't meet the assumptions, then you would look into the transformations of the data, retest the assumptions, and hopefully, and this is one of those places where I'll say hopefully after you do the transformation, everything's okay.
Or if you do the transformation and you still don't have problems with skewness or kurtosis, then your data is just junk.
Or it may be that you have a few observations that are influential, and
Outliers, maybe?
well, they may be outliers, they may be legitimate observations that need to be in the data, but we might look at using a trimmed data set. So knock off the top 3%, the bottom 3%. So there are different things we can do if we don't meet the assumptions. Also, if you don't meet the assumptions after doing those kinds of things, you would look on the non-parametric side and see what the equivalent non-parametric test is. So it's not hopeless if you fail the assumptions. There are things you can do.
Okay.
It's just, a lot of times, people assume they've met the assumptions because of how they collect the data.
Yeah. I'm at mud right now.
You're at mud?
Yeah.
Okay.
I mean, I understand it. It just isn't. I'm okay.
It's kind of like a tryout for, say, a sports team.
Right.
Not everyone gets on the team, so
Right.
people show up, they go through a tryout. You're either
Don't make the cut.
on the team or not on the team, or maybe you're told, okay, go away and do these exercises for a couple weeks and then come back and we'll try you again. That's kind of the way it is. You meet the assumptions, you're on the team. We can do the test. You don't meet the assumptions, we send you away to do some practicing, you come back, we see if you're able to be on the team. If not, we say, sorry, you can't be on our team, but hey, go over to Europe and they have this thing called football. Maybe you could play there.
Okay.
And so that would be, instead of doing the parametric test, we're moving you to the non-parametric.
Okay. better.
It's scary. Well, it's scary when I
I'm
use
better. I'm better. I mean, I promise.
It's scary when I use any sports analogies.
Yeah,
I was just looking at the same thing.
You did it right. You did it right.
Yeah, it's a lot to think about in terms of how everything fits together. Okay, so we can check our normality using the tests I just mentioned, or we can use the
Smirnoff.
yeah, Kolmogorov Smirnoff.
You got some?
What do you think's in the water bottle?
Yeah. Did you notice some of the water bottles have special notations?
So that's how you get through this
I
class.
know there's
That's how you get through comps.
When I was in grad school, one of the professors routinely taught his undergrad classes drunk. Yeah. The thing was, he was so intelligent that even drunk, he was smarter than 95% of the people in a room. So, yeah. Things you encounter at some universities, the big universities. Of course, at Michigan, you're always drunk.
You know what's happening today, don't you? Michigan, Ohio State.
Oh, really?
Who I said that word first. Oh, that game.
You feel dirty,
I
don't you?
do.
Yeah.
So I know where my brother-in-law is.
Yeah.
Right in front of the TV.
Yeah.
Okay, so we can use the Kolmogorov Smirnoff test. And the null is that the distribution is normal. The alternate is that it is not normal. So based on this, we have normal distribution. Null is distribution is normal. Alternate is that it's not. So based on our Kolmogorov Smirnoff.
So guess is less than alpha, so we reject null.
So it's not normal.
Yep, so the distribution's not normal, which is what we had concluded based on the kurtosis and skewness. And this is the distribution for all of the data combined. So this is just another way to check the distribution for normality. And then I ran it for the two groups the two subsets from earlier, classroom and none. So based on these, what about classroom? Normal or not normal? Normal, and why is it normal?
We failed to reject null.
Yep, we failed to reject the null, therefore it's normal. How about the none group?
No. Is less than an alpha.
Right.
So
So
we
it's
failed to reject null.
yep, so it's not
It's slightly not normal.
yep, not normal. And my guess is the skewness and kurtosis were probably somewhere right around 1.96. And this test tends to be specifically designed for detecting normality. So even though it's easy to get the skewness and kurtosis numbers, I would tend to rely more on this test for our normality assumption. But
Can you go over those two one more time?
the
classroom, when you fail, because it's outside of the number.
yeah, so for the classroom group, we have a significance of 0.122.
Right.
So
It's higher than your alpha value.
higher than alpha. So what does that mean in terms of the hypothesis?
You would fail to reject.
Fail to reject. And then the hypothesis was, the null is that the distribution is normal. So you failed to reject it, therefore you conclude it's normal. We failed to reject the null. So, and the null says the distribution is normal.
Okay.
Then,
Yeah.
for the none group, our significance level.
I see the difference in the numbers there. Has there ever been a case where one would say it was significant, the other one would say it's not, and how would you handle that in your data?
The one that I see people talking most about is this first one, so I would give that one priority.
Okay.
And it is possible that one would say it's not, one would say it is, like you said, because there's a bit of a difference between those two.
0.005 difference of being.
Yeah, and so there could be situations, but I would, without something telling me to go with the other one, I'd stick with the first one. So, Charles, is none group, is distribution normal or not normal?
No, because you would reject the null hypothesis and the distribution is not normal.
Yep, exactly. So this is testing
It's
normality.
not normal or normal?
Not normal.
It's not normal
Not normal.
because the P is 0.037, which
Because
means
you're
what-
basically taking the alternate hypothesis.
and the alternate is
Reject,
that it's
okay.
not normal.
Right.
So basically, for this one, we test normality. Once we know if it's normal or not,
I wrote those.
then we would know if we need to do any kind of transformations or if we're able to process the data as it is. So, normality. And I should mention this, normality is especially a problem with small sample sizes. So for example, let's say the Rayosoft says you should have a sample size of 400. I'm going to keep the numbers easy. So 400. And your sample size ends up being 100. That's a pretty big difference. And let's say you have 5 different groups that you're looking at. Now you're down to potentially 20 people per group.
And then you don't have the 30 that satisfies central limit.
Yeah, so you're in small sample size territory. And so if you get deviations from normality, you're probably going to have to transform your data or use a non-parametric test. And Kruskal-Wallis is one common non-parametric test for comparisons if you have normality problems. Now, if you have large sample size, say instead of the 400, you manage to get 500, and you get a small deviation from normality, probably, like, instead of it being greater than 0.05, it's 0.049 on the Kolmogorov-Smirnov test. Probably not going to need to do a transformation. But that hurdle is very subjective.
That's a huge sample size because using the formulas in Rayosoft or doing a manual, you hardly ever get over.
Yeah, I just made those numbers up so they're easy for me to keep in my head. So,
380s.
yeah.
Force that.
But